So now we have the 74HC14 here. So that's hex 6 NOT gates or inverters. Now there's Schmitt trigger as well. So there's not like a middle point where you're in an iffy region. But in any case, we have a low input. We actually have a low output. That's not what we expect. We expect the opposite. We expect a high output. And we have a high input. Now we have a high output. Again, we expect the opposite. But that's because we actually use 2 NOT gates right here. So we got an inversion of the signal, and then that gets inverted again. So ultimately you get out what you put in. So here you can see our output coming to the input there. We got the output. So this is going to be the opposite coming up there, and then it's going to opposite again, giving you what you started off with. So that's one reason why most integrated circuits you see when you got logic gates are like NAND, NOR, or NOT, because you can make other logic gates with them. So now here's the schematic diagram I put together for 2 NOT gates. They're Schmitt trigger though, remember that, wired in series so that they become a buffer. And I also have the pin layout, but you should check the data sheet of the particular one you're using for this information. I just put it for an introduction. So with 74, I have the HC14 right there. There's 6 NOT gates, and there's other information here, again, that you find on the data sheet, better than looking at this. So if we have a high input, I set the trim pot high enough, and accounting for hysteresis right there, we will get a low output at that NOT gate, which will be the input of the other NOT gate. So that will output high because it's the opposite right there. So high in, high out, pretty straightforward. Whereas if we give a low enough voltage here, we'll get a high output. Remember, we've got to account for hysteresis, but that's not a problem. So the high input now becomes a low output. So basically low in, low out.